Hello everyone, this is Dr. Dhiman and I welcome you all to this microprocessor tutorial series. So in this video we will learn about the memory read machine cycle timing diagram. That means we will learn how to draw the timing diagram for the memory read machine cycle. Okay, so here you have to understand two parts. One is the timing diagram, that is the graphical representation of an machine cycle. Okay, that is various data signals and as well as address bus, data bus signal. Okay, so we will represent various signals as well as the contents of the address bus as well as the data bus for understanding the memory read operation. So what we understand by memory read? Memory read means you have to understand that something is there in the memory. This is suppose the stack of the memory. Suppose we have 2000, 2001, 2002, 2003. Suppose we have 4 memory addresses, and if we have suppose 058, this is the suppose content. Then memory read operation means here we have the microprocessor MUP or the microprocessor. This is the shortcut for the microprocessor. When we read the memory, that means data will be this data. Suppose we want to read this data will be transferred to the microprocessor unit. So this is nothing but the memory read operation, and we have to draw the timing diagram for this memory read instruction machine cycle. Okay, so first of all we have to understand about various timing and the signal properties. So we have already discussed about the various operations. Here we have already discussed about the opcode fetch operation in details in our previous video. This operation we have already completed. Now in this video we will find out the timing diagram for this memory read. MR means memory read operation. So here you can see that for the memory read operation, as it is a read operation and RD bar is the active low signal, therefore we have a 0 value here. So this is very much important here. Write bar signal, this is the active low signal, this is not a write operation, therefore we will have a 1 value here. If it is 0, then it would have been the write operation. Input output or memory, when we are concerning with the memory part, then here you can see memory is the active low signal. Here we have to put a 0, and INTA means this is nothing but the interrupt acknowledgement. This has no relation with the memory read machine cycle. So we have already learned about the opcode fetch operation in our previous video. So please watch this video if you have any confusion about the opcode fetch operation in the microprocessor. So in this video we will take one example, and through that example we will see the timing diagram. Okay, suppose we consider one instruction. The instruction is suppose MPI. This is an immediate mode of instruction. Immediate instruction A, 32H. Suppose this is the instruction. Here we can see that this MPI, this is nothing but the operation. Okay, MPI means move immediate. If we have an I at the end in the opcode, what will happen? This is nothing but this is the representation that data is already available in the instruction. So here the data is 32. 32 is in hex code. This H represents the hex code. Okay, 32 is the data available in the instruction. Okay, during the memory read operation we have to load this data into the processor. Okay, this is the data we have to read, and here we have the accumulator. A, capital A represents the accumulator. This is the standard code for representing the accumulator. So MPI, it will have some opcode. Now what will be the opcode for this MPI instruction? Opcode, let me write down. Opcode will be equal to 3E, and this will be in hex code. This is the opcode for the MPI instruction. Okay, MPI operation, for the MPI operation 3E is the opcode. So we have to keep in mind. So let us see one memory unit. Suppose here we have the microprocessor, as we have already seen. So this microprocessor will have some memory addresses. Suppose this is the 2008, this is in hex code. 2001, this is also in hex code. 2002H, 2003H, 2004H. These are the various memory addresses in hex code. These are the memory locations. Suppose the program counter is pointing at this location. Suppose PC means program counter. Suppose the program counter is holding this memory address 2000H. Okay, so first of all, the opcode, let us assume that the opcode 3EH 3E is in this address, and in the next address 2001, let me show you with another color. Now let in this address 2001H we have the operand is here 32. So here we have two data. Basically, one is the data, that is the operand, and here we have the opcode. So in the opcode fetch cycle, we have to load this data to the microprocessor. This will come to the microprocessor during the opcode fetch operation, and during the memory read operation, this data will come into the microprocessor. There are basically two read operations, so you have to understand what is the difference between the opcode fetch and the memory read. In the opcode fetch machine cycle, we have 4 T states. The first T states are the read cycle, similar to the memory read case, and in the case of memory read operation, we have only 3 clock cycle, but the 4th clock cycle in the case of opcode fetch machine cycle, this is for the decoding of the opcode. So here we can see that this 3EH is the opcode for this instruction MPI, and 32 is the data. So in the first machine cycle, this 3EH will be transferred into the microprocessor, and the microprocessor will decode this instruction, that this is the move instruction, immediate move instruction, and the microprocessor will understand in the 4th clock cycle. That means during the first 3 clock cycle, the microprocessor will read this opcode to the microprocessor, and in the 4th clock cycle of the opcode fetch operation, this will decode this operation. This will decode and it will understand that this is a immediate move instruction, MVI. Okay, and 32 will be transferred during the second machine cycle, that is the memory read machine cycle. We have to understand in this way. So here 3EH, so what will be the machine code? This is one hex code and this is the opcode. So for this, what will be the respective binary number? 3 will be represented as 0011. We have to represent each of this hex code or hex digit, we have to represent it in binary form, 4-bit binary form. Okay, so E means it is nothing but 14, so this is 1110. This is E. Okay, this is the binary representation, or this is the machine code. We can write here machine code. Now we have the data is 32. So 3 is again 0011 and 2 means 0010. This is the data. Okay, this one is the data. Now we have to do some mechanisms, or we have to do some operations such that in the first machine cycle, this opcode is fetched into the microprocessor from the memory unit that is available in the 2000H location, and during the second machine cycle, the microprocessor will go to this 2001 memory address and it will find out and it will read the 32H or 32 hex code. Okay, in the second memory address. So how this microprocessor will perform? Now let us see with the help of timing diagram. So in the timing diagram, here I have taken this figure from the microprocessor book by Ramesh Kankar. Okay, so during the first cycle, we can see here during the first machine cycle, we have the opcode fetch operation. During this opcode fetch operation, as I have already explained to you, that it has 4 machine cycles. The first 3 clock cycle, the microprocessor will read the opcode. That means the microprocessor will read the opcode 3E. This one is the opcode. Let me use another color. The microprocessor will read this 3E from the memory, and in the 4th clock cycle, it does not read any information, but it decodes the opcode. Whatever be the perform it need to execute, it will understand the instruction code or the operation code. So we have this opcode we have already learned in our previous videos. During this opcode, let me briefly explain you. We have, these are the clock cycles. Its function is always represented in terms of its clock cycle. These T1, T2, T3, T4, these are the T states for the opcode fetch machine cycle. Again, for the memory read machine cycle M2, we have this T1, T2 and T3. These are the 3 clock cycles, or these are the 3 T states. T means here transition states. During these T states, there will be transition. Okay, during the clock, depending on the operation of the microprocessor. Okay, so this clock cycle is very much important for every type of timing diagram. This is must. This is the most important part, but in most of the cases this clock cycle looks similar. Okay, whether it is a memory read or memory write, input output read or input output write, whether it is the opcode fetch also, this clock cycle will look similar. Now let us understand about the A15 to A8. This is nothing but this is the address bus. So as the name suggests, it is the address bus. This address bus will always carry the address. Okay, this address bus is always used for the address purpose. Whenever we want to reach some memory location, the address will be transferred to the address bus. So here also one point to be noted, that A15 to A8, what do you understand? These are the higher significant bits. In the case of 8085 microprocessor, we have 16-bit memory address. From 15 to 0, we have 16-bit memory address. So the higher order memory address from 15 to 8, these are transferred to this higher order address bus. Okay, and we have AD0 to AD7. These are the multiplexed AD means address as well as the data. So this AD7 to AD0, these are the multiplexed address data bus. Sometimes it will carry the address, sometimes it will carry the data. Okay, so this second bus you have to keep in mind that this is a complicated one. Previous case this was the address bus, now this one is the address as well as the data bus. Sometimes on the time shared manner this will be working as a address bus, and in the time shared manner it will be working as a data bus as well. So in this case of address data bus, you have to keep in mind that the address latch enable signal will help us to understand whether it is a address bus or data bus. So whenever we have this ALE signal, this is the most important part in the case of latching the address data bus. So whether this address data bus will perform as a address bus or data bus, that will be dependent on the ALE signal. When the ALE signal has a high value, see here we have a high value and here also we have a high value. So whenever we have a high value in the ALE signal sent by the microprocessor unit, then the address data multiplex bus will be working as a address bus. Okay, so here also it has a address bus. Okay, and here you can see AD7 to AD0, that means the least significant bit LSB 7 to 0. These are the least significant bit. So this least significant bits will be transferred to this multiplexed address or data bus. Okay, so here you have to see that during the opcode fetch operation, also during the first clock cycle or the first T stage, both of these signal are high. Whenever ALE is high, this address data bus or the multiplex or the time shared address data bus will be working as a address bus. Okay, now in the first clock cycle in the opcode fetch operation, it is carrying the 00. From where it is 00 is coming, and here we have a 28. So these are the addresses, because during the first clock cycle the microprocessor need to send this address to the memory unit, and from the memory unit it will collect the data from that address. Okay, so here you can see during the first opcode fetch operation, this is the opcode. First of all, whatever be the content of the program counter, the microprocessor will find that address, or the microprocessor will send that address to the address bus, multiplex address bus, and as well as the address bus. So this will be sent to the microprocessor, and the microprocessor will increment the program counter content. That means whenever the microprocessor send this address 2008 to the memory unit, then after sending the address, the microprocessor program counter will direct towards the second memory address, that is the 2001. Now when we send during the opcode fetch cycle this 2008, this is the memory address, this is a 16-bit memory address, and the microprocessor 8085 A15 to A8, these are only used for the address, and AD7 to AD0, these are used for address or data. So when it will be working as a address bus, when it will be working as a data bus, that will be dependent on the ALE signal. Okay, so this higher order bits 2008 is the memory address. So A15 to AD0, this will be a 16-bit bus. So A15 to A8, this will carry the 20 higher order bits. Here we have this 20. This 20 is coming here. So this 20 will be carried out by this address bus, and this AD7 to AD0, this will carry the lower order address. This one, let me use another color. This 00 will be carried out by here. So here we'll have a 00 content. Okay, so the address bus A15 to A8, this will contain the 20 value, and this address data bus will contain the 00 value. So see here you can see, so 28. So one thing you have to keep in mind, that in the case of address bus A15 to A8, whenever we load something in the address bus, it will remain there for 3 clock cycles. Here also you can see 3 clock cycle it is remaining. Okay, in the case of memory read also we have 3 clock cycle it is remaining. Okay, so this is one important point you have to keep in mind. Okay, now in the fourth T state, here in the case of opcode fetch operation, this is unspecified, this is not known to us, and then the data bus in the first cycle it will carry the lower order address. Here you can see this is the lower order address of the 2000. Okay, in the 2000 we have carried the 00 value in the lower order address data multiplex bus. Okay, I hope up to here you have understood. And what about the input output or memory bar signal? Input output or memory bar signal will be low for the entire period. Why? For the entire period it will be low, because you can see this is opcode fetch is also a memory read operation. So in the case of memory read operation, it is not related to the input output devices. Therefore, as it is an active low signal, we have to keep this input output slash M-bar signal low to work as a memory read operation or the memory access operation. And in the case of opcode fetch, we have already understood that the signals are 1 1. These data signals are 1 and 1. Let me use another. These are 1 and 1. So we have to use these values here. For the opcode fetch operation, we have the S0 and S1. Both value are, let me use another color. These both values are having at one stage for the entire clock cycle. So this data signal has this S1 equal to 1 and S0 equal to 1. Input output or memory bar signal is 0 because it is a memory related function. Okay, now this read bar signal, because the opcode fetch as well as the memory read operation also, they both are the read operation. So after getting the opcode here, what will happen? This read bar signal will go low in the microprocessor. When this read bar signal will go low, because it is a active low signal, so during this period what will happen? The data will be loaded to the data bus. So during the opcode fetch operation, we have, this is the opcode. So during the opcode fetch operation, we have to fetch the opcode. We have found the memory. This is 20H and this is 00H. So this is a 2000H memory address. So after getting the 00H, the microprocessor goes to the 2000H. This is the memory location, and in that memory location we have this data available, and this is the opcode 3EH. So this 3EH will be collected to the microprocessors through the address bus. Okay, so this 3EH will come to the microprocessor. When the microprocessor receives this opcode up to this 3 clock cycle, in the 4th clock cycle, this is a high impedance state. Okay, this is unspecified in the address bus. So during this period, what will happen? The microprocessor will decode the opcode. That means the microprocessor will understand what performance or what operation it is going to perform. Okay, so this is all about the opcode fetch operation. Now let us see about the memory read. The memory read is also similar to the opcode fetch operation. Only the difference is that we have 3 clock cycles here. We have 3 clock cycles. There is no decoding because this is not the opcode. This is the immediate data. In the case of memory read, it will read the data available in the instruction. So in this instruction, we are already having the data available in the instruction. So this is the given instruction, and 32 in hex code, this is the given data. So we have to read this data. Similar to the previous cases, we have to go to the memory location. Now that this data 32 is contained in the memory location 2000H. Therefore, after program counter sends this 2000H to the microprocessor or to the memory unit, the program counter content will be incremented by 1 plus 1, so it will go to the 2001H. This is the memory location. Now the program counter is counting. So after completing the opcode fetch operation, this memory address will be accessed. So during this access memory, this is 20H will be transferred to the A15 to A8, and the 01 will be transferred to the multiplexed address database. So here you can see, so in the memory read operation, during the first T state, here you can see, during the first T state, what is the higher order data? 20H. And what is the lower order data? Or the LSB 01H. This is the memory address. It has been transferred to the memory unit through the microprocessor address bus. Okay, address as well as the address data multiplex bus. And here you can see the ALE signal is high. That means the AD7 to AD0, this one is working as a address bus during the first clock cycle, and during the second clock cycle you can see ALE signal is low. That means now the AD7 to AD0, this is working as a data bus. So during the second clock cycle, after some high impedance state, we have the 32H data. So after going to the memory 2001H, the data available in the 32H, this will be transferred into the microprocessor unit. This will be coming to the microprocessor unit. So here you can see this microprocessor keeping the RD bar signal low, that is the read operation. So during this time period from here to here, this data has been loaded into the microprocessor databus. Now this data is available in the databus of the 8085 microprocessor. So during this T2 and T3, this operation will be now completed. There is no decoding operation because this is the immediate data. Okay, so in this way you have to see. Now in the second case, you have to see here that input output or memory bar signal. Okay, so input output signal, this will be always low. This will be low because you can see here, this is the memory read operation. When we have a memory read, input output or memory bar is the active low signal. Whenever therefore we have to perform a memory read operation, we have to keep this signal low. Here we can see this is 0. Okay, and what about the status signal S1 and S0? So let us now see the table. So here I have made a mistake here. This one is 1 and 0. Okay, this will be 0 and 1. This will be 0 and 1. So in this way we have to modify the remaining also. When it is a read, we have to make this is 1 and 0 and 0 and 1. 1 and 0, 0 and 1. These are the correct values. Now we have S1 and S0 values. These are 1 and 0. So we have to make this S1 and S0 because it is having the both the signal. Therefore S1 and S0, this will be having, suppose S1 will be traveling through this line, it will be represented by the above line or the high line, and this S0 equal to 0, this will be represented by the lower line. So this lower line will represent the input output / M bar signal 0 as well as the S0 signal equal to 0. These are the status signal. Okay, and during this read period of this data, this read bar signal will be low because this is the active low signal. So in this way we can understand the memory read cycle in the case of 8085 microprocessor. Thank you for watching. If you have any question, please put it in the comment section below. Also like, share and subscribe to my channel. Thank you.